Think of your thermostat. You give it a temperature, it checks the current temperature, then it turns on the heater or the cooler accordingly. Single input, single output, and simple. Now a drone, however, is much more complex. It's got to read a gyroscope, it's got 4 rotors to balance, and it's also got to probably send a camera feed to your phone. And that's multiple inputs, multiple outputs. Now you can model a simple system easily, but the problem is, how do you model a complex system easily? And the answer is state-space linear systems. And that's what we're talking about today. Now, chances are, if you clicked on this video, that you know a little bit about control systems. It's hard to miss if you studied electrical, computer, mechanical, or aerospace engineering in college. But if you haven't, control systems is basically where abstract math collides with physical dynamics. You can already imagine why that would involve a lot of modeling. So I'm not going to bore you with the details. I'm just going to show you how state-space linear systems are the standard for modeling in modern control systems. To understand why this method is king, we have to travel back to the late 1950s. The space race was heating up and engineers were struggling to guide rockets using classical control theory. And back then, they relied heavily on the frequency domain. With a system like that, you knew what went in and you saw what came out, but you didn't know what's inside. That inside is called the black box. When you're doing something simple, it's not that bad. When things get as complex as rockets, though, it becomes a nightmare. Around 1960, a brilliant mathematician and engineer named Rudolf Kalman changed everything. He basically said, let's open the box and describe what's inside, calling it the state. For example, in a moving car, the states could be its position and its velocity. Thanks to him, now we can use linear algebra in the time domain, so there's no need to transfer into the frequency domain anymore. A few years later, in 1963, UC Berkeley professor Lotfi Zadeh and Charles Dessauer published the first textbook on the subject. This breakthrough taught a huge incoming wave of engineers to stay in the time domain, and modern control theory was born. When we're building a state-space linear system, we have the input function u, which exists as a vector of real numbers of size k. A state function x, which exists as a vector of real numbers of size n, and an output function y, which exists as a vector of real numbers of size m. Notice how all 3 of those depend on time? Let me teach you the term continuous time. That means that time is an element of all the numbers from 0 to infinity with no breaks in between. Every infinitely small number right after another. State-space linear systems have 2 equations, the state equation and the output equation. In continuous time, they look like this. The state equation is an ordinary differential equation, and the output equation is a nice and easy, as you see it on the screen. These are called the system parameters. If system parameters rely on time, we call the system a linear time-invariant system, or LTV for short. However, if system parameters don't rely on time, we call the system a linear time-invariant system, or LTI for short. There is another type of time called discrete time. That's when you treat time as an element of the set of all natural numbers. This way, we don't have to worry about every infinitely small value between, for example, 0 and 1. In discrete time, the state-space linear system equations are a bit different. The state equation is like so. Notice how this isn't an ODE, it's a difference equation. The output equation is pretty much the same. Check out this video on how easily you can model a state-space linear system using block diagrams. Thanks for watching SciPK. I'm PK, and I hope you don't mind my little cowlick today. It was really annoying to film with. But if you enjoyed the video, please like and comment. I'd really appreciate it. And as I grow this channel, I get to show you guys cooler and cooler things. So if you want to be a part of that journey, please subscribe. I'd highly appreciate it. And as always, stay curious.